Well, hello students and others interested in learning and understanding how the analysis of variance test works. I want to start by reviewing what the t-test does for us. And so the t-test is used when we're comparing the two means of two sets of measurements, and we want to know if those two means are different or not. And so if you remember, with the t-test, we are testing basically what's called the null statistical hypothesis. And in the case of the t-test, because we have two sets of measurements, our null hypothesis is that the two means that we have generated are equal. And any differences between those two means are likely to have occurred by accident or by chance. That goes against what's called the alternative hypothesis, which is that the means are in fact different. And so different that we can say they didn't occur by chance, and these differences are real differences. So we're wondering in the t-test if these two means, if the differences between them are statistically significant. And here is the equation for the t-test. And so here I have the difference between the two means, and if we are expecting a significant difference between those two means, then we expect this difference to be large. And we can call this the signal. And underneath this difference is what's called the standard error for the t-test. And we can call that the noise. And that's basically all of the variance and the error within all of the measurements that you've made in these two sets of data. And so what we end up with is we end up with this single number, single statistic called the t observed. We can call this the signal to noise ratio because it's a ratio of the signal to the noise. And we also in the t-test get a probability that's returned as a part of the statistics. And the probability is the probability of generating a t observed of a particular magnitude by accident if the null hypothesis is true. Now, if the probability of getting this number here is really small, then that makes this expression unlikely. And we can reject this idea, and we can accept or conclude that the alternative hypothesis, that the means are different, is much more likely than the null hypothesis that they're the same. And so that's the t-test, and the t-test compares two sets of data to each other. The analysis of variance is used when we have more than two sets of data, more than two sets of measurements. And so over here, you see I have the same two sets over here that I had with the t-test, same numbers, same means, but I've included another one that I'm comparing them to. And it's a little more complicated, because now I have three means that I'm comparing, and so to generate the signal for these three means is a little bit more complicated. And to generate the noise, all the variance within all the measurements, is more complicated. The null statistical hypothesis for the analysis of variance is that all of the means are equal. And so here I've got my three means, but it could be 4 or 5 or 6 means that I'm comparing. The alternative to that is that if you can see here, I've got an unequal sign between these two means and an equal sign between this mean. So the analysis of variance just detects whether or not there is a significant difference between at least two of the means of all of the means that you're comparing. So at least one mean is significantly different from the other means. And so if I look at my means here, I might hypothesize that these two means, the difference between them could have occurred by chance, and these two means aren't different, but this one looks very different from the other two. So that's why I put this unequal symbol here and an equal symbol here, just for this particular example that I'm using. And then, of course, we have the probability that's generated in the analysis of variance. So this, just like the t-test, is the probability of generating a statistic. In this case, with the ANOVA, it's called the F observed, generating this statistic by accident if this expression is true. if the probability of getting this statistic is really, really rare, and in this case less than a 1 in 20 chance, then this expression is likely not true. And I can reject this idea, and it makes this alternative hypothesis that at least one of the means is significantly different from all of the others. This becomes more likely. And I have what's called a treatment effect in the analysis of variance. So back to the F observed. The F observed is also called the F ratio, and it's because it's a ratio of a statistic we generate called the mean square between, which in this case is our signal, just like the t in the t-test, the difference between the means is our signal. Here our signal is the mean square between divided by the noise, the mean square within. And over here is a table called an ANOVA table. And so here I have my source of variation. So I want to know how much variance there is between these three means. And I want to compare that variance, that noise here, which in this case I'm calling the signal, to all of the variance within all of the measurements. And so the first statistic I calculate in the analysis of variance is called the sum of squares, otherwise known as the sum of squared differences. It's very similar, in fact it's identical to adding up all the squared differences in the t-test. And so let's back here to the ANOVA. So a squared difference in the case of this first set of data would be the difference between this measurement 11 and its mean squared. That would be the squared difference. And then the squared difference between this measurement 9 and the same mean. And then I would add up all of those squared differences and get what's called the sum of squares, or the sum of squared differences. And that is what you see here. So this number, 67.4, is the sum of squared differences between each of these means and the overall mean for the entire set of measurements. So if I add up these three means and divide by 3, I will have what's called the grand mean, or the overall mean. And that's where I get this sum of squared differences, or sum of squares, this 67.4. The sum of squared differences within are, if I were to add up all of the squared differences for every single measurement in all three sets of data. If I add all of those up, then I can get the sum of squared differences within the entire set of measurements. And so to get to my average sum of squared differences, the mean square, I have to divide by the degrees of freedom. And so between these three sets of measurements, since I've got three sets, the degrees of freedom between them are 2. 3 sets of measurements minus 1 gets my degrees of freedom of 2. My within degrees of freedom is calculated by adding up all of the measurements here. So I've got 10 measurements, so that's a sample size of 10. Minus 1 gives me a degrees of freedom of 9 for this first set of data. Here I have 10 measurements again. Minus 1 gives me my degrees of freedom for this set. 10 measurements, minus 1 gives me my degrees of freedom here. So that's 9 degrees of freedom plus 9 degrees of freedom plus 9 degrees of freedom equals 27 degrees of freedom within all of the measurements. And so if I divide 67.4 by 2, I get my mean square, or my average sum of squared differences, which is 33.7. So there's my signal. And if I then divide my sum of squares within 123.8 by my degrees of freedom within 27, I get 4.6. There's my noise. Notice that the signal here, 33.7, is much larger than the noise. And so if I'm expecting that at least one of these three means is significantly different from the others, then I would expect a large signal, in this case 33.7, and very little noise, in this case 4.6. So if I divide 33.7 by 4.6, that gives me my F observed, my F ratio, my mean square between divided by my mean square within, my signal to noise ratio. And in this case, it's 7.3. Now, when you do an ANOVA in, say, a spreadsheet program like Excel, or if you find an ANOVA calculator online, and there are many of them that do this, you often will also be given the critical F value. And so this is a number that that will be generated 1 out of 20 times if this relationship is true. So you should be able to get an F ratio of 3.3 1 out of every 20 times if you get differences by accident. And so if your observed F value is larger than your critical F value, then you can conclude that this was likely not by accident. This 7.3 can only be generated accidentally less than 1 in 20 times. And so I can conclude in this case, with this analysis of variance of these 3 sets of measurements, that I have a significant difference between at least one of the means and all the others. And it's likely this one right here, this 8.7. And that's called a treatment effect. So I can conclude that whatever my response variable was, I got a significant effect of that response variable based on whatever independent variable I was using.